Yeah, so okay, we're going to talk about transactions and the blockchain today. We're going to have 2 lectures. But first, I want to talk about the course itself. Maybe I probably didn't pronounce this correctly or enough yesterday, because this course is mainly theoretical. So we will do very little practical exercises. So it's all theoretical. But we will have some labs on Friday where you will be able to set up your own Bitcoin full node. And also you will be able to send some test coins between each other. So that's going to be fun on Friday. But until then, it's only theoretical. And I also want to say that there are answers to all exercises in the second appendix of this book. So just scroll down to the very bottom of the book and you will find answers to the exercises there. So if you are in doubt, I suggest that you go to the answers just to. So this is about the course. Yeah, I see some stuff in the chat here. Okay, the first question here is, since running a full node takes a lot of time, about 3 to 4 days, can we perhaps run the installation a little earlier? Well, we are not going to run on the main network because I want you to send coins between each other and I want them to be test coins. So we are going to run something called Signet, which is a network for testing, and it's exactly the same as proper Bitcoin, but it's not real Bitcoin. So it's a separate network from the real Bitcoin, but it's the same. It's the same anyway. But this blockchain is very small, so you won't have to spend days to download the blockchain. It will take a few minutes only. So that's not really an issue, but thanks for asking that. Can you explain, someone asks, Shubham asks, can you explain in brief about deriving hardened private keys again, please? Yes, we can do that. So if we take this summary picture here and using the extended private key, you can derive any child extended private keys, both hardened and non-hardened. And for each extended private key, there's a corresponding extended public key. But the difference between hardened and non-hardened extended keys is that if someone steals this public key here and this private key here, if this is hardened here, they will not be able to derive this private key here. But if this is non-hardened, they will be able to derive this key here. But regardless if this is hardened or non-hardened, if someone gets this extended public key and this private key, they will still be able to derive all the keys under this private key here. So hardened derivation isolates accounts from each other. That's all there is to it. And of course, if you want to look deeper at how that's done, you can go back to these illustrations here. But the effect is a subtle difference of what you can do if you get certain pieces of information. If you get a sub key and a sub private key and some parent XPub, what can you do with that information? You can do less with that information if hardened derivation is used. So, as the schedule says, it's time to talk about transactions. We'll do a very quick recap. We started out with this very simple spreadsheet with names in it, And we replaced the names with the public key hashes. So Lisa and the messages to Lisa were emails where the recipient was a public key hash and the sender was a public key. And this message was signed using the sender's private key. And we talked about addresses, how addresses are created from a random number generator, created a private key and a public key, hashed it to a public key hash, and encoded that public key hash using base 58 check encoding to get the cookie token address. And these addresses always start with a 1, and there are a lot of, after that, there's a lot of base 58 characters. And we talked about extended private key derivation schemes like this, and how these are useful for backups. So when you generate your seed, you do it in 2 steps. First, you generate a mnemonic that you store in a safe place, and then from that mnemonic you generate the seed, and from the seed you generate the tree of keys. So let's talk transactions and a big problem. Lisa has ultimate access to this spreadsheet. She can do whatever she likes with it. She can steal. She can steal in multiple ways, really. If there's an existing payment to Lisa, like this one here, Lisa can just go here and simply edit the numbers. She can change 10 to 30 here, and she can also add new rows as she pleases. She can just add a row that steals 40 cookie tokens from John to herself. And this is no good. People don't like this. Of course, Lisa has been very trustworthy. Everybody trusts in Lisa, and she's doing a great job. But some people are feeling pretty uncomfortable about this situation. And as the company grows, Lisa might be pressured to do this for other people, or for herself. She might weaken in her trustworthiness. Okay, so this is no good. She can steal. Everybody wants to stop this from being a possibility in the first place. So we're going to start to use something like transactions. And the idea with transactions, one of the ideas with the transactions is that the transactions include the signatures, so that everyone okay, I'm backing up. We have instead of the spreadsheet, or we replace the spreadsheet with just a spreadsheet of transactions like this. So the spreadsheet now contains only transactions, but the transactions themselves contain information about what money to spend and where to send them. And they also include signatures of the sender, which is important, because then anyone who reads this spreadsheet can verify that the sender is actually authentic. Okay, so the new process here is from the wallet perspective, it's the same as before. You scan someone's address and you click OK, and the wallet will select keys to use for the payment and create, instead of an email to Lisa, it will create a transaction that it sends to Lisa, a special formalized, it's a formalized message that they send to Lisa, and Lisa will verify it, and if it's okay, she will add the transaction to the spreadsheet. The transaction points, the transaction needs the transaction spends money from previous transactions. So it has, well, I'll show you that later, but each transaction must spend money from previous transactions. So we'll have a look at that, how it looks. So on your left here you have a number of transactions that I zoomed in on a bit. Let's call them transaction 1 up here and transaction 2 down here. And then when John wants to buy a cookie from the cafe, he needs to create a new transaction like this on your right. And if we look closely at this transaction, you can see that it has a left side and a right side. The left side of that transaction, of John's transaction, contains inputs. And the right side contains outputs. Inputs are referring to previous transactions' outputs. So if we look at the first input here, it contains a hash and a number. This is an index. So this hash is actually the double SHA-256 hash of the transaction to spend from. So when John creates this transaction, he hashes this transaction that he's going to spend from and adds the hash to this input here. And this 1 here refers to the index among the outputs in that transaction. So 1 refers to this, the second output of the previous transaction. And this is 0 based. So the first output is indexed 0, and the second output is index 1. Okay, so this input refers to an output of a previous transaction, an already existing transaction. Okay, so and then the second input, in the same way, it refers to a previous transaction through its transaction ID. I'll talk more about transaction IDs later, but transaction ID is just the double SHA-256 of this transaction. A transaction ID is used to refer to transactions, and it's the hash of that transaction. So this input refers to output 0 of this transaction here. And then we can look at the outputs. This transaction has 2 outputs. The first one is 10 cookie tokens to the public key hash of the cafe. So John is buying a cookie here. So he needs to send 10 cookie tokens to the cafe, and this is what this output is for that payment. And then we have another output here, which seems odd, but if we look at the inputs, we are consuming a total of 13 cookie tokens. You have 8 cookie tokens here in this output that's being paid to John. And here we have 5 cookie tokens being paid to John in this output here. So in total, those two are sums up to 13 cookie tokens. So John is spending 13 cookie tokens here. And he sends 10 cookie tokens to the cafe, which means that there are 3 cookie tokens left. And for that reason, John will add a second output containing those 3 cookie tokens. And we call this a change output. So this is a payment back to John's public key hash. So John has this public key hash, and he sends the cookie tokens, the 3 cookie tokens, to himself. So this is just like going to the store and you pay something with you pay 10. You're paying $7 dollars to the cashier with a $10 bill. So you need to get $3 back from the cashier. So it's called a change output. And I said that transactions aren't contain signatures too, and they do, but this doesn't contain a signature yet. As you can see, the previous transactions here, the already existing ones, they do contain signatures, but this doesn't yet. He will sign it shortly. So this is the general data structure of a transaction. It spends inputs and it creates new outputs. And the notion of a transaction ID is very central in Bitcoin, which is the double SHA-256 of a transaction. Okay, so now John is about to sign this transaction. You know, he has these 2 coins that he's going to spend. And as you remember, each public key hash is associated with a private key that John has. So in order to be able to spend this input here, spend this output here, he needs the corresponding private key, which is this private key here, which belongs to public key hash 1. So he takes this full transaction here as the message. This full transaction is the message, and this private key as the private key. And so those 2 things are the input to the signing algorithm, and he signs it and puts the signature, not yet, but he keeps this signature around, and he also needs to put the public key here. But he doesn't put it here yet. He waits a bit because he needs to create signatures for all inputs first, and then he can add all signatures. So he just creates those signatures, this signature, and then he does the same for the second input. He uses the private key that belongs to this public key hash 2 here, and signs the transaction with that private key to create a signature. And then he inserts the signatures and the corresponding public keys into these inputs here. And you might wonder why the public key is needed here. It's for the same reason you had the public key in the message to Lisa before. It's so that Lisa can verify this signature here. Lisa doesn't have, if this public key is not included, Lisa can't verify this signature. And of course, Lisa can verify that this public key that she finds here corresponds to this public key hash here. That's also very important. Okay, so let's have a look at the spreadsheet again. You have this spreadsheet, and we're going to talk about something called the unspent transaction output set, the UTXO set, which is also very central in Bitcoin. Lisa keeps a data structure that she calls a UTXO set, which is a table of outputs and the transaction ID and index, output index. So when Lisa receives this transaction from John here, this is the new transaction that John created, and these are the old transactions that are being spent. So Lisa keeps this UTXO set, and in this table, she keeps all unspent transaction outputs that are available in this spreadsheet. So in this case, we have, if we just look at John's 2 spent outputs, we have this that spends 8 cookie tokens, sends 8 cookie tokens to John's public key hash. And for this output, there is an entry in this UTXO set, which is the transaction ID and the index ID, or the index, and the output itself. So this is a table of all coins. This is who owns what. This is the table of who owns what, more or less. So if someone has any coins, it's available in this UTXO set. So let's look what Lisa sees here. When she gets John's transaction, she can look up these transaction IDs and indexes in the UTXO set to verify that John has the money to spend. She will look up this hash and this index at this row here and see that there is an output belonging to this public key hash, which corresponds to this public key. So she can be sure that there is money to spend here. And the same for the second input. So let's have a look how Lisa would verify the first input now. She has this UTXO set here, and she takes the first input and looks up the corresponding output in her UTXO set. And she would take the public key from the input and hash it using RIPE-MD 160 and compare that with the public key hash in the UTXO set. If that matches, it's all good. It's good. Let's move on. If it's good, we will verify the signature. She will verify the signature. And as input to this verification, she uses the message, which is the full transaction. The full transaction is the message, the public key, and the signature from this particular input. And if this signature is okay, then Lisa knows that this input is actually valid. And then she does the same for the second input as well, which, well, she'll do the exact same operations, but for this row in the UTXO set instead. Okay, so that's how Lisa would verify the transaction. And if it's all okay, she will add the transaction itself to the list of confirmed transactions, the spreadsheet. And she will also update her UTXO set. She will delete the UTXOs that are now spent because they are not unspent anymore. This is it's an unspent transaction output set. And since these two are not unspent anymore, she removes them. But she also adds 2 new unspent outputs. One for the cafe and one which is his change, John's change. So this is how Lisa would manage her UTXO set. And this is very important in Bitcoin too. And we were trying to solve the problem that Lisa can steal. So she can't do that anymore now because the signatures cover the whole transaction. And if she goes in here and changes numbers here, those signatures will become invalid. And Lisa doesn't have the private keys to spend these outputs, because only the rightful owner has the private key. So Lisa can't do anything about the transactions themselves. So she can't just go in and change numbers as she pleases. So we have moved the system from what we call an account-based system to a value-based system. The spreadsheet as we had them before was a value-based system, and the spreadsheet as it is now is a sorry. The spreadsheet as we had them before is an account-based system, and the spreadsheet as it is now is a value-based system. And an account-based system means that you have accounts with amounts in them, and those amounts can be deducted and added to. So when you move money, you deduct from one account and you add to another account. But in a value-based system, you have coins, more akin to physical notes and coins, where you delete spent coins and you create recipient coins. So you take coins out of your pocket and you give them to someone else. The general idea is that you have coins of various face value, and you can destroy them and create new coins which sum to the same amounts as we saw before. So we have moved from an account-based system to a value-based system. And I wasn't totally honest with you before. The output doesn't just contain a public key hash. The output actually contains a small program, a small computer program, if you will, which we call a pub key script. And the input that spends the output is called a signature script. And that provides input to the program in the pub key script. So we'll go through this in more detail, but this is what makes Bitcoin programmable money. It's a very common meme to say that it's programmable money. And this is the reason for that. The output contains a program, and the input contains input to that program. So we'll see in detail. If we zoom in on this output here, we can see that it's a small program that starts with opdupe, op hash 160, pkh1. This is the actual public key hash. And then you have an operator called equal verifier, verify, and op checksig. So these are instructions to Lisa for how to verify the spending of this output. And if we zoom in on the signature script, it's just as it's written here. It's just a signature and a pub key. But it could be operators there as well, but it's very, very uncommon. Okay, so this is the pub key script and the signature script together forms a complete program with input. We will run this program step by step to see what actually happens here. But yeah, so the pub key script contains a program, and the signature script contains an input, contains input to that program. Okay, so we have this a program here, the total program, and it's a stack-based program. The language is stack-based, which means that you have the program and you have a stack. And we'll take it step by step. You start with the top item of the program here. And this is just a data item. A signature is just data. And so you move that data to the top of the stack. And the next item is also just data. And if it's just data, we move them to the stack, to the top of the stack. Maybe I should pause and see if there are questions. No, we'll take that afterwards. Adi may interrupt me if there are any questions. So, yeah, so we have pushed 2 items to the stack now, and the next thing in the program is an op dupe. An op dupe just takes the top item from the stack and duplicates it like this. So we have duplicated the top item, and the next operator or the next thing in the program is an op hash 160 operator, and that's an operator to hash data, hash the top item with SHA-256 and write MD160, which is the same operation that you do to create a public key hash. So you hash this public key, the top public key here, and you put the result back. And this result happens to be a public key hash now, right? And then we encounter next item here, which is just data. It happens to be a public key hash, which it puts on top of the stack. And then we have the next item, which is op equal verify. And it will take the top 2 items from the stack and compare them. And if they compare, all is good. If they compare, this operator succeeds. If they don't compare, this operator will fail. And then we have the last operator in the program, which is op check sig. And check sig will take 2 items from the stack. It will take a public key, and it will take the first item from the stack, which it expects to be a public key, and it will take the second item from the stack, which it expects to be a signature. And as input, it will use the transaction. And the transaction itself is not on the stack, but it's around, it's in the context of this checksig operator. So it will use these 3 inputs here to verify, and it will put the result back. In this case, the result is okay, true. So it will put okay back. And now the program area is empty. And we have a single item on the left, on the stack, which is true. And if the program is empty and the stack has a non-zero item on top of the stack, it will regard the program as successful, the program as a whole as successful. So if there's a non-zero element on top of the stack, it will accept the program. The program has succeeded. So now whoever verified this, for example, Lisa, Lisa has now run this program here, and the program terminated with OK, which means that Lisa can trust that whoever has this public key here, she can trust that this spending of this output is authentic. Lisa actually doesn't care what this program is here. She just runs the program, and this particular program checks that this public key matches this public key hash, and this signature and this signature is valid for this message and this public key. Yep, so I've explained a bit how the output contains a program and the input contains input to that program, and I walked you through how this program is run to verify the spending of this output. And Lisa, when Lisa verifies this transaction, she has to run all programs for all inputs here. For all spent outputs, she needs to run this program. So we're going to talk a little bit more about more advanced scripts and a new address type that's introduced in, I think it was 2012 or 2013, called pay to script hash instead of pay to public key hash. We'll talk about that. We'll come back to the address format itself later and talk about advanced scripts in general right now. So suppose that Faiza, Ellen, and John has a charity together. They have created a charity for which they collect funds from people. So they want people to support their charity. And how would they collect money to this charity? They could do it like this, that Faiza creates a wallet for herself, and she keeps her private keys private to herself, and then she creates an address like this and asks people to send money to this address here. But that has some problems because Faiza can run away with the money. Ellen and John has no control over that. And Faiza can also die and take her money with her into the grave. So this is not a good way to solve it. It would be better if Faiza, Ellen, and John can share both the responsibility and the power over the money. So we will take an example here with something called multi-sig. So this is a 2 of 3 multi-sig setup. Suppose that Faiza has one private key, Ellen has one private key, and John has one private key. And wouldn't it be great if they could share, or it would be great if no one could run away with the money. So to spend their money, it would require 2 of these 3 people to sign a transaction. So either Ellen and Faiza signs a transaction, or Ellen and John signs a transaction, or Faiza and John signs a transaction. In that way, no single person can sign on their own. They need someone else from this organization to sign as well. And this also means that if Faiza would die here, Ellen and John still can spend the funds. And no one can run away with the money on their own. So this is a pretty common and good setup. So this is a very common scheme in Bitcoin, especially if you have serious amounts of funds. So this is where pay to script hash comes in. Yeah, so we'll start on the top left here, where it says please support us, and a QR code, which encodes a new type of address, which starts with a 3 followed by a number of base 58 characters. So the key here is that it starts with a 3. If it does, we know it's a pay to script hash address. And pay to script hash, resembles pay to public key hash, but instead of paying to a public key hash, you pay to a script hash. And I'll show you in detail what that means. So if someone wants to pay money to this address encodes a script hash, a hash of a script, which is 20 bytes. So this hash is put in the outputs. So this is a donor transaction. Someone wants to send money to their organization, and they send 3 cookie tokens to this script hash. And when Faisa and John wants to spend this output here, they need to provide the actual script here, just as you would need to provide a public key in the legacy transaction, or in the pay to public key hash transaction. You would need to provide a script in the signature script. We call that the redeem script. But let's zoom in on this a bit. We look at the pub key script here first, and that's in the program area down here. So it contains op equal followed by the script hash and op hash 160. That's the full program so far in the pub key script. And in the signature script, you have, first of all, you have a redeem script, which is a program that would require 2 or 3 signatures. And this script, the hash of this script is this script hash down here. So that's important. And further, after this redeem script, we have 2 signatures and a 0. We will go through this in detail. But the important thing to take away here is that this script here, the redeem script, if you hash that script, it should be the same hash as you have down here or up here. So let's run this program then. This is a bit more complicated than the pay to public key hash version, but we'll manage, I think. So as we used to do before, we take items one by one from the program area and do the appropriate thing with them. So the first item here is a 0, and that's just data, so we put it on the stack. And the next item is a signature from John, and we put that on the stack, and Faisa's likewise put it on the stack. And then we have the redeem script, which is also just a data, because it's it's a packaged script. It's just you can view it as a file containing a script, and this file is just a file. It's just a piece of data. So you put that data on the stack as well. And then you take the next item on the stack, which is op hash 160, which is hash the top item with SHA-256 and ripe MD 160. So you take the top item, you hash it, and you put back the result on top of the stack, which is the hash of the redeem script. And then you push the next item to the stack, and then you run this op equal, which is compare the top two items on the stack and put the result back on top. Now, you would think that the program area is now empty and it's okay on top of the stack, which means this program was successful. Yes, it would be. It is for a node that for a wallet or for a node that doesn't understand pay-to-script hash. That would be true. As I said, pay-to-script hash was added in 2012 or 13. I can't remember which, but somewhere there, pay-to-script hash was added. But there was already, at that time, there were already a lot of Bitcoin software out there who didn't know anything about pay-to-script hash because their software was old. And to keep old software compatible with new software, they had to make this change in a forward compatible way, so that new transactions would work with old transactions. New transactions would be valid on old nodes. So this is a pretty quirky way to do it. You could do it in a better way if you could do whatever you want without taking old software into account. But now we have to take old software into account, and we don't want to break compatibility with those with that old software out there. So this is what an old node would do. It would run the program and just see that when the program area is empty, we have OK on top of the stack, which means the program succeeded and the spending is OK. But a new program, a new software would be aware of the pay-to-script hash type and recognize that this program here is the pay-to-script hash pattern. So if the software recognizes this pay-to-script hash pattern, which is op equal and 20 bytes of data followed by op hash 160, that's the pay-to-script hash pattern. If it recognizes that pattern, it will, after this step, it will remember, it will save this stack here at this third step and do some extra stuff. So it will take this top item. This is new software that's aware of pay-to-script hash. So it will take the top item and unpack it into the program area like this. So the redeem script is this program here. I will go back to this picture here. As you recall, this redeem script is this program right here. Yeah, so so it unpacks this redeem script onto the program area, and then it starts to run this redeem script. And as always, we push data items to stack. So we push the 2 down here, and then we push John's public key here, Ellen's public key here, Faisal's public key here, and a 3. Okay, and then we have the op check multi-sig operator, which does a lot of things. But this operator, first of all, it pops the top item from the stack, which is a 3. And that means that it expects 3 public keys from the stack. So it will pop 3 items from the stack, which are 3 public keys. And then it will pop the next number, the next item, which it expects to be a number, the number of signatures to pop. So it takes this 2 and then expects 2 signatures. So it pops 2 signatures, and then it finally pops this 0 here. This 0 is actually a bug in Bitcoin. This 0 doesn't do anything or doesn't provide anything of value. It's just there to satisfy a bug that expects a 0. Okay, so one moment, please. I have to. Ja. Vart? Stockholm? Just det, ha det så bra. Hej. Okay, sorry. I had to say goodbye to my daughter. Okay. Yeah, so this 0 is a bug. Just ignore it for now. We won't talk more about that. Okay, so it has taken these 3 public keys and these 2 signatures, and it will verify that at least that these 2 signatures are valid for this transaction. And so it will verify both signatures independently, and if they both are valid, OK is put back on the stack. And now the program is empty even for this new software that's aware of pay-to-script hash. So what we have done here is a soft fork, really. This is called a soft fork. When you create a change, when you change the rules of Bitcoin in such a way that the data from new software is also compatible with the old software, and that's called forward compatibility. So the old software will not make these checks, of course. Old software isn't aware of this. So old software will not check this program. It will not run this program here. So it's actually much less secure. It just checks that the redeem script matches the one in the that the redeem script matches the script hash. That's all it does. It doesn't run the redeem script itself. But we will come back to how that can actually work. It sounds horrible to let that happen, but it does actually work. And we will come back to that in chapter 11. So we will leave that for now because it's pretty advanced right now. We will talk about it in chapter 11. Okay, so let's talk about the rewards to Lisa again. Just as before, Lisa used to add a row in the spreadsheet every day with 7,200 new cookie tokens. And Lisa will do the same now, but in a slightly different way. She will instead add what we call a coin-based transaction to the spreadsheet every day. And this coin-based transaction does the same thing. It creates 7,200 new cookie tokens every day. But it's in the format of a transaction. And you call it a coin-based transaction. So the output is 7,200 new cookie tokens. And the input should contain a transaction ID here, but it's a coin-based transaction defines the transaction ID to be zeros, all zeros. And the index is -1, and the signature script can be anything. It doesn't matter. So this is how Lisa rewards herself from now on. This will change further in the next chapter. So later today, we will change this a bit. So looking at how transactions are organized, a transaction spends previous transactions. And this will form a graph of transactions like this. So you have a transaction graph, and each input can be traced back to one or more coin-based transactions. Coin-based transactions are the only ones that doesn't refer to previous transactions. So if you follow any chain of inputs, any chain of transactions like this, you must always end up at the coin-based transaction. Otherwise, something fishy is going on. So this is the transaction graph. So to recap a little bit, a transaction contains an output, and the output contains a pub key script, which is the condition for spending this output, the program that exactly depicts what's needed in order to spend this output. And the signature script satisfies the spending condition of the pub key script. And then we have pay to public key hash, which is the legacy address format. We talked about that yesterday, pay to public key hash. And we talked about pay to script hash today, where you can do more advanced things. And finally, we talked about the coin-based transactions that Lisa uses to reward herself. Hang on, I need to. Yeah, so now, as we said before, Lisa can't steal anymore. But we still trust Lisa to not delete transactions. And we also trust her to not censor transactions. So she can't go into the spreadsheet now and change existing transactions. She can't make changes to the transactions because they are signed and the signatures are public in the transactions. So anyone can verify these transactions. Anyone with read access to the spreadsheet can verify that the transactions are valid and the signatures in them are valid. So Lisa can't change numbers in the transactions anymore. But she can delete transactions and she can censor transactions. We will come back to these problems in later lectures. The next lecture will prevent Lisa from deleting transactions. And the lecture after that, which will be about proof of work, will prevent Lisa from censoring transactions. Okay, so we will now run the breakout sessions for 40 minutes, and you will do all the exercises of chapter 5. And this was, again, quicker than I thought. So, yep, great.